This is a dramatic reading of Deriving the Maxwell Source Equations using Quaternions, the second of a series of 5 focusing on field equations, by a blog by the Stand-Up Physicist, available at science2.0.com. The Maxwell source equations will be derived using Quaternions, an approach James Clerk Maxwell himself tried and yet failed to do. As far as I'm aware, this technique is not in the literature up to an isomorphism. Now, meaning that it actually is there, just under a different name, math in disguise. By using Quaternions, the approach can be extended to generate field equations for particles for the weak and the strong forces, with the symmetries SU2 and SU3. The extension is a technical speculation, which I define as precise math whose applicability to nature I don't really have a clue. Now, warning here, we're really doing classical field theory calculations in detail, which just requires much more math than is customary, like ever, in public. You know, you can do this as a problem, but don't really show it. But, well, we are going to actually do that sort of thing here. So, let's actually start with the biggest possible picture. That is to define what the Maxwell equations accomplish. The Maxwell equations detail all the space-time changes in all the space-time changes in a space-time potential created by massive particles in a space-time current density mediated by particles that contain no notion of their own history, photons living in now. The Fab Four of equations has stunning staying power, riding from the 1860s through special relativity, general relativity, and quantum mechanics, unaltered. Those who have played a part in the ensemble grunge band The Standard Models know that they perform covers of Maxwell using louder groups in their Marshall stack of PR amps. Now, out here on the ultra-conservative fringe, I have zero tolerance for the new age noise that uses strings. Time for Dorothy to go home to Kansas field theory. No Maxwell, no physics. The next 4 blogs use the same 3-part harmony in the steps. The first step is to define the Lagrange density. This step needs careful contemplation. Why should this particular small set of symbols dictate the actors on nature's stage? Given her creativity, completeness is a requirement. The second step is to run the one Lagrange density through the 4 Euler-Lagrange equations to generate 4 field equations. This is a graceful math machine whose details are rarely revealed in public due to the investment required to draw out all the gears and levers behind the curtain. There will be a visual component to this exercise to limit the level of detail needed to see the Euler-Lagrange equation in action. The third step is to pick a gauge to reorganize the variables on the bookshelf, making the results look so neat and tidy that they can actually be committed to memory. Lagrange density, Euler-Lagrange, choose a gauge, rinse and repeat. Quaternions are going to be used to define the Lagrange density for the Maxwell source equations. A quaternion is just a rank 1 tensor in 4 dimensions that comes equipped with multiplication and division. Now, here are the rules for multiplication, since, quaternions have been blacklisted by the folks who write textbooks, math textbooks. So you just take the first guy times the first guy minus the last, and then the vector part is outie plus innie plus the cross product. And I actually capitalized letters that happen to be three products. Three vectors. All right? So that's it. That's all you got to learn. First minus last, innie, outie, cross. It's not so bad. Okay, so now we're going to construct a complete set of first order changes of a space-time potential using quaternion multiplication. Okay, so what do we have here? So we've got at the start a derivative with respect to time, and then that del thing is derivative with respect to x, y, and z, so that's space. And then we've got a forward potential that's made up of that scalar phi and then an a. And you multiply those things together, and you do first minus last, so that's d phi dt minus del dot a. Okay, that is known as a gauge term. And then for the vector part, it's outie, innie, cross. So outie is dA dt, innie is grad phi, and cross is curl of A. Great. And those are the electric field and the magnetic field that show up so often in physics. So is the electric field showing up and the magnetic field just showing up? Is that just luck? Oh, well, you know, I'll take a pair of aces down as my cards, but you know, it's like the simplest thing that you could do with a quaternion derivative and a potential, which gives me the most important field theory fields in physics. That's incredibly nice. So some might actually complain about that gauge term that was in the beginning. Now, there is a time and a place for gauges. Specifically, it's going to be the last blog in this series. This is not actually the time nor the place for the gauge. So why don't you just subtract those terms into what I call empty time oblivion. I'm calling it time because I always associate that first term, that scalar, with time. So 0 time, that's empty time, you know? And, you know, we've completely erased the gauge. And because we've done that, photons are allowed to fly at the speed of light c. They have no history to tell. And this is one of those, you know, physics facts. I kind of accept the connection between not having a gauge term and going at the speed of light. And I haven't quite yet developed a pithy pitch for a broader audience. I'm sorry about that. Now, those who barely are in the know about quaternions complain that quaternions don't commute. You know, it's like, oh my God, that's so bad, that's so evil. And it's like, you know, lots of other things have that property too. Everything I've ever touched spins in some kind of way, and the spin has that kind of property, you know, quantum mechanically and classically. So that bug actually sounds like a feature to me. But let's actually counterattack. So let's calculate the fields with the order reversed, okay? So putting the potential first and then that differential operator and see what happens. And what we get is the same two fields. It's only the B field that happens to change its sign. Now, whiners will weasel that we don't know which one of those two to use. And the definition of the Maxwell equations discussed earlier makes the answer clear. To be complete, we must use both. So actually, let's go ahead and multiply them both together. And what we get out of that process is b squared minus e squared as the scalar. And we get 2 times this curl thing of the E and the B field. Now, while this might look complicated, the zeros in the front actually make it actually pretty easy to do because the first term is the negative of the product of the two. It's basically the two lasts, as it were, while the vector part is all cross product. The Lagrange density is the Maxwell, the scalar there is the Lagrange density for the Maxwell source equations, that first term there, the difference of two squares. The Poynting vector, which describes energy density for the EM field, shows up free in the vector term. Like everyone but Poynting, I'm going to actually ignore it. The difference between squares terms is invariant under a rotation. Rotate how you look at this thing, and B still points in the direction of B, while E still points in the direction of E, so B squared minus E squared doesn't change at all. I'm struggling to find out why a boost would leave this difference unchanged. I mean, everybody says it, so I'm just flopping around looking for personalized explanation of that particular technical detail. So let me give you a little summary and foreshadowing here. There are two ways to take the quaternion spacetime derivative of a spacetime potential. Two orderings of those two factors. Eliminate the gauge term either way so that things travel at the speed of light. Take the product of the two. The Lorentz invariant scalar is the Lagrange density of the Maxwell source equations. A different combination of the two ways to take the quaternion derivative of a potential will yield the the Lagrange density for the Maxwell homogeneous equations in the next blog. The Lagrange density B squared minus E squared needs to be written out in its component parts. Bummer. Because there's a lot of detail there. This exercise has a lot of similarities to a Sudoku puzzle. There are some factors that show up exactly one time per column, and there are other factors that show up like 2 times per row, and the patterns can be used to check for errors. So let's start simply, because that's exactly the same thing you could do in Sudoku. So write out only Bx and Ex. Multiply those two together, and then clone those patterns for By and Ey, and then the values for Z, those got to be fixed by all those other results. Now, I can't actually recall what Bx is, other than it doesn't have X's in it. I mean, I have to go back to something I learned in high school. This was high school level kind of electromagnetism that I kind of remembered. Oh, I, J, K, and then the 3 derivatives, and then the AX, AY, AZ, and you go down that row, so you get this DAZ dy minus DAY dz. So it's the DAY dz term that's positive. I literally have to do that nearly every time. So the electric field Ex, that I can recall. Okay, they have 2 terms. They're both negatives. They both have X factor. So that really kind of limits to what it can be. And that looks like it's spot on. It's minus dAx dt and minus d phi dx. Okay, so what you do then is you go ahead and square those. Okay, so here is the Bx squared. And so, we actually didn't have to, I realized this when I was kind of writing up some notes. You don't actually have to remember which one is positive and which one's negative, because you're going to square it. So you get the square of the dAz dy and the square of dy dz. Oh, I can see I made a mistake here. That should be a... No, this is right. This is right. I was looking at the monitor over here, and the monitor is wrong, and I had to go correct that on the website. Yeah, so those are both squared. They're both positive. Now there's a mixed term there. It's got a minus sign, okay? And it's got a minus sign because one of those terms is positive, the other is negative. So when you multiply those, the cross terms will be negative, all right? Napkin is correct. When you do the same thing for the EY term, kind of a similar structure. You know how you get the squared terms and you get a cross term, but because they both have the same sign, the cross term is going to be positive. That rocks. Okay. So you basically subtract, and here's basically the entire collection. There's the BX and EX terms that we wrote out, 6 terms in total, 2 cross terms, 4 kind of squared terms, and then you do the variations on Y, thinking through, oh yeah, the BY thing's not going to have either an, it's not going to have any Y in it, so it'll be X and Z, and then of course the Y terms, you just put in all those Y's in there, and then the BZ stuff, it's very similar. It's going to be made out of, the B part is going to be made out of X's and Y's, and it's going to have squares and a cross term that's the opposite sign. So, you know, you can actually use Sudoku-like rules on those columns to check that my work actually is spot on or not. And the current coupling term that goes into the Lagrange density is actually quite easy by comparison. So in another blog, I actually showed how the vector part of that term actually implies a spin 1 particle is doing the work here. And a spin 1 particle mediates forces where like charges repel, which is perfect for EM. All right, so one last detail. You need to throw in a factor of 1/2 in the difference of the squares of the two fields of B squared minus E squared. So with all these parts in place, here's the Lagrange density written out in terms of its components. Now there are 22 terms there in all, 18 plus 4 there, all right? So now we just drop these 22 terms of the Lagrange density into the Euler-Lagrange equations, which have 20 slots to fill. Ouch! Don't try to do anything all at once quickly. That never works out, you know what I mean? We're going to set up actually some ground rules first, because there turns out to be an awful lot of repetition in this Lagrange density and Euler-Lagrange machinery. So we're going to have to start with the 2 and only 2 bits of calculus that you're actually going to use over and over again in this in the next 4 blogs on working with fields. Even if you have never taken a calculus class, these are often the very first 2 rules that you learn because, well, they're simple. So we're going to start with a simple function like f times f equals x times y, okay? X can be anything, y can be anything, and this function is really just the product of the 2. So in calculus, what we want to know is how the function f changes as x is varied. And you say, but there's really only one x there, so really won't it just be plain old y? And in fact, that is the case. Okay, so you can see I've written up there that function f equals x times y, and then the derivative, that's what that df dx is about. The derivative of f with respect to x just equals y. So that's not so bad. Now, what if y happens to equal x? Then the function is now x squared, and I call that g just to be different, just to be clear. And you might first guess, well, won't that be just like the other one? It'll be just like x. Well, no, there's that factor too. So this actually changed because there are 2 x's. That almost like makes sense, right? There are 2 x's, so how this changes is 2x. And that's actually all the calculus you're going to need to derive the 4 Maxwell field equations and my 2 variations. So there are situations where something simple sounding ends up being like really, really hard. For example, like, what is inertia? We still don't have a solid answer about that one. And then there are other situations that look really, really hard, but are simple. You look forward to those, you know, because you can impress people with that sort of thing. So it is actually the second case that happens here, time and time again. Instead of a simple looking factor of x, we put in a complicated looking thing. And even though it's complicated looking, it still turns out to be this, you know, x squared goes to 2x sort of calculus party trick. So let me just show you an example of that. Here we go. All right, so here x is equaling d phi dx, all right? And we've got this function h, which we're saying is 1/2 d phi dx squared. And so now I want to take the derivative of the h thing, which has got all that stuff in it, with respect to something that's really kind of the stuff. And it turns out to just be d phi dx. I was like, oh, well, that wasn't so bad. And now you can kind of see why I tossed in that factor of 1/2 earlier, because it meets the 2x part. The half meet a 2x, therefore you just get unity out of it and you just get x back. And so let's just take another brief look at that Lagrange density. It's really complicated looking, but it's really all these x, y's, and x squared sorts of animals in there. And there's actually nothing other than those two. And the Euler-Lagrange equation effectively plucks these out. And actually it does slap on another derivative in front of it. So the Euler-Lagrange equation turns out to be a second order derivative factory. That's what it does. It says, you give me all these squared things and I'm going to end up giving you back second order derivatives. And there turn out to be no factors of 2 because they all politely wipe out. So to derive Gauss's law, that is one of the Maxwell source equations, one works with any term that has a phi in it. And all other terms can be ignored. Ah, thank goodness. So we can see that there is a one term that's got a phi living in the what's called the current coupling term. And then there are these derivatives, and they all live over on the right side. Okay? To a mixed derivative term and what I call a pure squared term, as it were. So, you know, in the mind's eye, go ahead and erase one of those terms having a phi in the highlighted area, and you're actually going to have to take a derivative, usually with respect to the with respect to the thing that's there right now. So if there's a d phi dx squared, you're going to get a second order derivative of phi with respect to x. So now we're going to apply the Euler-Lagrange equations, and we can see that we end up with this relation down near the bottom where we have all these second order terms, okay? Now, these results can actually be written in a simpler way, and this is the gauge games that I'm playing right now. So when defining that Lagrange density, the time derivative of phi and the divergence of A were like wiped out by an act of subtraction. Now, we are thus free to pick any relationship between the two at all, since that won't change this calculation in any way. So here is something called the Lorentz gauge. All right, it's got the minus dAx dx minus dAy dy minus dA dx dz equals d phi dt. So you can actually substitute that in there, because there is a minus dAx dx, a minus dA dy dy, and a minus dAz dz in there. And when you do that, you go, oh, we get a little miracle happening. Oh, it's on there. Sorry. That the whole expression becomes rho, the charge density, equals the second order time derivative minus the second order space derivative, basically. And they even abbreviate that a little bit more with something with that box squared, which is called the D'Alembert operator. All right, cool. So let's just summarize the results. that we take this Lagrange density written in a nice compact way, and we're going to take parts that have phis in them and end up at Gauss's law. So this is the no shortcuts way to derive the Maxwell Gauss's law kind of equation. Now we're going to repeat this process, this time focusing on any term with an AX, ignoring all others. Well, they're kind of spread out over the place here, but they're easy enough to pick up. And we see, you know, basically there's one per line. There's one in the current coupling term, well, a pair in each of the subsequent lines. One in the kind of E part of the graph, and the two others are in the B section, the B squared section. So they do live in different places, and it is good, though, that they do that, because that means we're going to get like complete coverage of this Lagrange density. So again, try and erase things in the mind's eye, things with the AX terms, and think about, oh, which one doubles up. It's a little tricky, but it can be done. So then we write these terms out, you know, so hopefully figure out what the summary statement is. The dx ex dt, I think, is doable. It's really not. It's not trivial to pick out the curl of A, okay? It's a detail that one works through as a grad student in physics, which I suppose most of you aren't. But instead, notice how it has the look of the curl of a curl, you know, the shifts, the variations of x's, y's, and z's. So let's just summarize this whole thing. We collect all these terms together, and we end up with Ampere's law about this, at least along the x direction. It's going to be a similar darn story for y and z. So I'm not going to actually show this in detail, but one can actually choose to work in that Lorentz gauge again, and then it also rearranges nicely to just be the vector j current density equals the D-Lambertian operator box squared times the vector potential. So we can actually compare the derivation of Gauss's and Ampere's law. And we can see that Gauss only involves the E field, and Ampere does involve both. And what's really fun about this visualization is that you can see things that you might miss in the pure algebra approach. For example, there's an overlap between Gauss's law and Ampere's law involving the mixed terms in the electric field squared. That would mean the guy's kind of in the middle of the 1, 2, 3 sort of E squared. And Ampere's law hits the magnetic field mixed terms twice as well. And all the pure squared terms are actually visited only once. So that's what you get for visualization. Now, how can we adapt this work to cover the symmetries of the weak force, the unitary quaternions, given that I've claimed that every one of these is a quaternion? Well, it's good that we figured out how to derive things, because if we look at the start of the first in this series, how to deriving how to derive field equations, which is the Euler-Lagrange equation, this was step number 1. Start with the Lagrange density. Now, this must be one that depends on potentials and changes in potentials. A Lagrange density does not have to have that property, but those are the ones that we're using. All right? So we want to study a variation of this. We want to start with the Lagrange density. Okay, but this one must depend on the normalized potential and changes in the normalized potentials. So, of course, a Lagrangian doesn't have to do this. So if I draw it on a napkin there, all I'm saying is that instead of depending on A, I depend on A over the absolute value of A. Instead of depending on the changes in A, I look at the changes in A over the absolute value of A. So that's kind of cool, because we would do our 7-step derivation, which I did in that other video, and we'd end up with a law that looked awfully darn similar. Okay? Except that, you know, we don't have A's anymore. We have A's over the absolute values of A's. All right? Now, in all this kind of Wikipedia level reading and discussion of the weak force I've seen, I've never actually seen a differential equation associated with the weak force. The discussions have always focused on symmetries and the fun ways that the weak force likes to break such symmetries and lead to Nobel Prizes. Those are really highly valuable insights. And yet, when I take a look at the covariant derivative of the standard model, which you don't see written on sides of buses or anything like that, well, you've got the B field, you've got the stuff for the weak force and the stuff for the strong force. I'm not going to go into too much detail, but there are things like current coupling constant, that's the G, and then the Y there, the tau, and the lambda. Those are generators of group symmetry, fancy name for things that do the work of U1, SU2, and SU3. And then those B, W, and G, those are actually potentials with different numbers of things in there. But the point of looking at this is that they're really kind of similar, okay? And I mean, the pros know this, you know, we're just changing the groups, okay? So if you're just changing the symmetry group, you know, I mean, why isn't there like an Ampere's like law, you know, for SU2 and an Ampere's and a Gauss's law like thing for SU3? I mean, I can't answer that. I think there should be. I mean, that to me looks so similar that there should be a similar kind of proposal. So why don't I just write out the Lagrange density for the weak force, and you can tell what I did. Wherever there was an A, I put in an A over the norm of A. Ouch! I mean, that's kind of scary looking. But there is a simple concept here. Every darn term necessarily has a unitary quaternion symmetry SU2. And so now I will repeat the derivation of the field equations using the unitary version of the Euler-Lagrange equation. No. This has gone on way too long. You know what the results look like. They're going to look kind of like Gauss's law and Ampere's law. And so to get the strong force, I do the following swap in both the Euler-Lagrange equation to make that apply to this situation, and the Lagrange density. I'm going to go from a nice simple one-letter A to A star over the norm of A and B over the norm of B. Why did I do that? Because this definitely has the norm of 1, right? Both of those things have 1. That star is absolutely essential because without it, I would just get the same symmetry as I had before. This has a different multiplication table is a fancy way to do it. And as to, well, why does nature care about this? Because if A equals B here, this comes out to 1 every single time. Not 1, I mean 1, 0, 0, 0. Okay, that kind of 1. And my sense is that what is going on in all this really hard math, let's face it, you've seen some really nasty Lagrangians. This must be really hard to actually work with, okay? And I don't quite know how to work with it myself. But the point is that it's about 1, looking at the symmetries of 1, 0, 0, 0 in a very sophisticated way. And if that is the case, then we will end up with a whole bunch of if we would now work in the Lorentz gauge, we'll end up with these kinds of equations. We'll have the Maxwell source equations, which is just this J equals box squared A. And then we might have these weak field source equations where both things are normalized, and the strong field source equations, okay, which has got this A and B thing, A star and B star sort of things. Now, that top line, now that is rock solid. I mean, that is in the official canon of physics over, more than 100 years, okay? As far as I can tell, the field equations shown in the second and third ones there for the weak and the strong, no. Those are technical speculations on my part, and I really don't know how to connect them with any sort of experimental data. I just know they feel logically solid, but that's not enough. It's a technical speculation at this point. So, to anyone who's lasted this long, gotta congratulate you on making it through. So, 2 of the 4 Maxwell equations are down, as it were, and the method for getting the rest has actually been set up. That would be write down your Lagrange density, apply Euler-Lagrange, do your field equation, do your gauge to make things easier. So all we got to do is crank it up and go. So here's my snarky puzzle. This blog was just too long, too much math. So let's make the author suffer. Let him figure out why b squared minus e squared is invariant under a Lorentz boost. All right, thank you very much.